All right, folks, at this point we have learned how correlation coefficients work, both the logic behind them and how to calculate them. And we've covered at least one example of how to calculate a correlation coefficient with a data set. But again, most of what we do in this back half of the class revolves around these hypothesis tests. These are how we don't just describe the information we get in the sample, we use it to try to understand these much larger populations. So we're going to talk a bit about how hypothesis testing is done in a correlational context. So first things first, again, hypothesis testing with statistical correlation. First, you're going to use the same 5-step model we've been using for the last several modules. You should be seeing that thing in your sleep if you're keeping up with this material. So we have the same 5 steps, but just like in a lot of other situations, we're going to do slightly different things at some of these steps. First, the first step is define our hypotheses. We still have those two boring hypotheses. We're going to do nothing but two-tailed tests from here on out in correlations. So it's pretty straightforward. It's those very common uh, hypotheses of equality and difference. But here's the big change. Every other hypothesis that we've talked about, research and null hypotheses, they've always revolved around mu's. Those population parameters that we're trying to compare have always been population means. Here, though, we're not dealing with the average score on a variable in one population compared to another. We're looking at whether two different variables are related to one another at a population level. So we have a different parameter we're interested in. We here now are trying to estimate or draw conclusions about the population correlation, which looks like this little kind of funky lowercase p, but it's a lowercase rho. So R and rho. R is a sample correlation. We can use it to estimate rho, which is a population correlation that we might actually be interested in. So just like we use sample means to estimate population means, we're doing the same thing in this context. So here, again, it's boring old two-tailed tests. We have our null, and our null just in this case is that the two variables are not correlated in the population. The alternative is just that they are, and because it's two-tailed, we don't specify in what direction they differ from one another. So the only real change here is that we're not using mu's anymore, we're using that rho. All right, so next, step 2, we determine the characteristics of our comparison distribution. That is a step we've been doing for quite a bit, but here we kind of get streamlined a little bit. We have to name the shape of our distribution, which involves calling it an R distribution, also calculating degrees of freedom. Degrees of freedom with correlations are the number of people that you measured minus 2. It's a real curveball here. Instead of subtracting 1, you got to subtract 2. So not really any harder to calculate, but you have to remember that that's the formula to use, and again, it'll be on your formula sheet in your exam. But why minus 2? Well, the reason why is that there now are two variables being measured, so the degrees of freedom jumps from n minus 1, as it was when we were just dealing with the same dv, just different groups, to n minus 2 to account for those two variables. The mean of that R distribution needs to be provided, but it's always 0, at least in this class. It could be specified to be something else, but in this class we'll stick to the basic version. The mean is 0. You don't have to calculate standard deviation or standard error, anything like that. It doesn't really matter. It's not an important part of the process. So now we just are defining the shape, which means naming the distribution, providing the degrees of freedom, and the population mean, which in this class is always going to be 0. So the mean rho, you would say, in that case, is 0. So then we find our critical value, and again, we have a table that you might have to use to look things up on our class examples, but on an exam, I'm just going to tell you what it is. But here we have an R table, which again is available in this module. It looks something like this. We use the alpha level that we set. Notice we have different alpha levels here. We use the number of tails that determines which place you look in, and then our degrees of freedom, which again is n minus 2. And we can see our significant correlations here. One thing you notice, the higher your degrees of freedom are, means you're measuring more people. The closer to 0 your significant correlations become. And again, just like with everything else, you measure more people, those comparison distributions get narrower and narrower, and you don't need to be as far away from the mean to be in that most extreme 5% or 1%. Step 4, get our sample score in the comparison distribution. That involves calculating R, like we covered in the last video. And then just like every other time, we compare our obtained R, the actual correlation, to our critical R's. And if it's beyond those critical scores, we reject the null. And if it's not, we fail to reject it. So let's walk through an example, and then we'll move on. So a couple of researchers a few years back were interested in looking at laboratory measures of aggression. Aggression is hard to measure in the lab because you can't really do it. You can't have people actually committing like violence in a way that's ethical. That's not really compatible with the IRB, compatible with getting research approval. So you can't have people like whacking each other with sticks or shooting each other with guns in the lab. So you have to find indirect ways of measuring. One of those ways is how much hot sauce people allocate to another person in a taste test when they're told that other person doesn't like hot sauce. Seems a little silly, but it's one of the common ways of representing it. Let's say we wanted to figure out if this is a good way of representing aggression. Something we might do, and what these researchers did, they take that physical aggression measure, that hot sauce measure, they also give them an established measure of aggressive tendencies as a trait. So they give them a questionnaire that's been known to assess people's actual aggression levels. We want to correlate them. If they are positively correlated, we are going to conclude that this lab measure is a pretty good way of representing aggression. So here's what they did. They collected data on 22 people. They used an alpha level of 0.05 and a two-tailed test, pretty common, to see if those variables are significantly correlated or not. And again, if they are, that suggests that these two measures are tapping into the same construct of aggression. If they're not, it suggests that they are measuring different things, which would be bad. So here's how their hypothesis test worked. First, they had to state their hypotheses. Again, the null was that these two variables are not correlated in the population, that rho equals 0. The alternative is that they are correlated at the population, that rho does not equal 0. So the null is that they aren't correlated. The alternative is that they are. Step 2, determine the characteristics of the comparison distribution. We have an R distribution with 20 degrees of freedom. How did I get that? Well, there's 22 people in the study, and I subtracted 2. And the mean of that distribution of R's, that distribution of correlations, is 0. So again, the mean rho is 0. So we're just providing shape and mean here. Find the critical value. Well, you can look at it by scanning down here. We have 20 degrees of freedom, alpha of 0.05, two-tailed test. We see 0.423. Because it is a two-tailed test, it's plus or minus that number. If in step 4 we get a correlation coefficient that is either greater than 0.423 or lower than negative 0.423, we're going to reject the null. If we don't get one outside of that range, beyond those critical values, we're going to fail to reject it. So here is step 4. Step 4, we get our sample score. We calculate the correlation coefficient. I'm going to skip over the actual calculations. It's a pretty big data set anyway, and just say that they found their correlation coefficient was 0.44. Then we make the decision to accept or reject the null. Is it beyond that threshold of plus or minus 0.423? Yes, it is. It's just a tiny bit over the line, but that doesn't really matter. We have enough evidence to reject the null. Trait aggression is significantly positively correlated with the amount of hot sauce that we send out to these other participants, which indicates they're measuring the same thing, which indicates that that hot sauce measure is probably a pretty good measure of actual real-world aggression. All right, so that's the end of hypothesis testing using correlation coefficients. Next up, we'll talk about some secondary stuff, how correlations are used, and some of the flaws of utilizing correlations. See you in that one when we will wrap up the module.